Hi, in this week, we gonna look at shortest path problems. Um, it's we'll discuss greedy algorithms with application in graphs problems. Last week we work on problems that require greedy algorithms. Today we will continue on using greedy algorithms, but with more on application in graphs problems or problem that involve graphs. Okay, there will be 2 weeks related to greedy algorithms and graphs problems. This week we discuss shortest path, and next week we'll discuss minimum spanning trees. Okay, so let's have a quick review on graphs and shortest path. We work on graphs problem before, right? Previously, our graph is usually is unweighted. Okay, so let's look at this problem. Okay, so suppose you're here in the morning and you would like to go to school here. This is your goal. Okay, and you would like to find a way to reach the school. But the time it takes for you to go from one node to another node is say is 1 unit. Okay, so if you look at this this path, so a path is a sequence of nodes with adjacent edges. So this is one possible path. It might not be a good one. Okay, and if each edge has length 1, this path will takes the length of this path is 1, 2, 3, 4, 5, 6, 7, 8, 9, 9 edges. So nine steps. So it takes you 9 steps to reach to the school. But this is not the shortest one because you can let's look at another. So this might be shorter. Okay, 1, 2, 3, 4, 5, 6 steps. But if you look carefully, you can see that this is shortest one, right? 1, 2, 3, 4. There isn't probably another shorter one, but maybe. Okay, to find a shortest path in this case, when the graph is unweighted. Okay, when the graph is unweighted, so basically you would like to find a path with the minimum number of edges. Okay, you can use the algorithm that we've written before, which is breadth first search. You start with this vertex, and okay, and you this is the first layer, right? And then what this is adjacent to this vertex is gonna be in the second layer, this one. So the distance from the starting vertex is 1. Okay, and everyone adjacent to this vertex like this is gonna be in the second layer. So who's gonna be second layer? This one, this one, also this one, and this one. So let me do that. Okay, so this is the second layer, and the third layer is gonna be like this guy. Okay, and finally the last layer is gonna be this one. So since this is our source, and this is your destination, target. So, and it's in the 4th layer, so there's a path of length 4 that take you from the source to the sink. Okay, like that. Okay, so when the graph is unweighted, we know how to solve the shortest path problem using breadth first search. Okay, however, the problem that we are gonna look at today is the case when the graph is weighted. Okay, what does it mean by what do you mean by weighted? So let's look at another example. Okay, so in this case, it doesn't it takes you maybe longer to travel on some of the path. Okay, so if you take the same path as before, like this, it's not going to take you 4 units of time. It's going to take you 13 plus 15 plus 20 plus 10. and that's really long. Okay, there are shorter paths. Okay, so how long is this path? It's gonna be 13 plus. So the length depends on the length on the sum of the length on the edges. Okay, so that's 58 units. But there are shorter ones. Maybe let's take a look at another path. Let's say the top one. The length of the top one is let's try to compute. It's going to be 3 plus 5 plus 2 plus 9 plus 3 plus 2. So that's 24. Okay. The shorter ones. Okay. I think the shortest one is this because I draw it. So maybe this one. Might be a little bit wiki. Okay, so this part, the length is can be 3 plus 2 plus 1 plus 4. And this is 18. Okay, so this is the shortest one. Okay, all right, so we'll discuss on how to find this path. You see how we would find this path using the Dijkstra algorithm. Okay, I'm gonna discuss Dijkstra algorithm as a way to generalize this breadth-first search. Okay, we'll look at small example first, and then to see how the idea from breadth-first search becomes the Dijkstra algorithms. Okay, and we discuss on how to implement it really quickly. Okay. Okay, so let's take a look at this example. Okay, can we use breadth-first search to solve this problem? In a way, if you just do the breadth-first search, we start with the level 0 here, right? And then this will be level 1. But the distance between this guy and this guy is going to be, instead of 1, it's going to be 3, right? So it's not that easy to, you cannot apply breadth-first search directly to it, okay? But there's a way to somehow build a new graph that simulates the actual that allows you to use a breadth-first search. Okay, so here's how I'm gonna do it. Okay, so I'm gonna make a copy of this first because I'll come back to it later on. Okay, so because this edge is of length 3, okay, so I'm gonna add 2 extra nodes there so that it's like the edge of length 3, right? So the edge become a path of length 3, and this also. So let me add new vertices so that I can basically simulate the breadth-first search with that. Okay, so if the length is 4, I add 3 extra points. Basically, it's gonna be like that. Okay, and now what I'm gonna do is like I'm gonna just use breadth-first search directly with the new graph. Okay, so if you recall, so let me try to label it. Okay, so this is the guy in the level 0, and then the guy in the level 1. This one, this 2 guy, level 1, right? And the level 2 is gonna be this one, this node. Okay. Okay, and level 4, let me come back to green. Level 4 is going to be this node, that node, and this one. Okay, you can see that this is level 0, this 1, 2, and 3, and so on, right? So if you continue like this, so let me try to do it until it's to the end. Okay, so okay, next layer, you can see that from here you can also reach this guy, right? So draw to that. Okay, and then the third layer is okay. Then I reach this guy. Okay, and let me write the layer number here. This is layer 0, 0, 1, 2, 3, and 4, 4, 4, then 5, then 6. So the distance from, can you guess the shortest path? Okay. Shortest path is probably this one. 6, 5, right? 4, right? And then here, this one, 1, 2, 1, 2. Okay, so the distance is 6. So here, let me highlight it here. This is the shortest path. Okay. All right. So you can basically use breadth first search. Okay, but you need to modify the graph. But this is not quite easy. It cannot be easily done because the edges can have weights, right? Here you have 20, right? So you need to create like a bunch of nodes there, and you know, it will be really inefficient to do so. Okay, so how can we simulate the breadth first search? This is a breadth first search on modified graph. So can you do the breadth first search on the modified graph in the actual graph without having to modify it? Okay, so the Dijkstra algorithm can be viewed exactly like that. Okay, so the way we're gonna do that is like, let's focus on the case when we arrive at the vertex. What I mean by arrive at the vertex is this. So you start with the vertex here, right? And then this next you go to this vertex with length 1, right? But you wait until when would you reach this vertex? Okay, you reach this vertex the same time as this, right? You basically have to wait. Okay, you reach this vertex first, and then you need to wait a little bit more until you reach this vertex. Okay, but if you are at this vertex, you know exactly if this edge is of length 3, you know exactly like the time that you reach this vertex through this edge. Say if you reach this vertex at time t, you know that if you go to on this edge, you reach this vertex at time t plus 3, right? And basically you can you can simulate on how the breadth first search goes in this graph using priority queues and whatever thing that you have. So let's take a look at that. Okay, so let me try to do that. Okay, and then we'll change that so that you get the Dijkstra algorithms. Okay, so this way of looking at Dijkstra algorithm might be different from the approach that you have in class, but I think it's easier to understand, and yeah, it leads to a way to implement it really nicely. Okay, all right, so let's do it. Okay, so I'm gonna simulate this on that, and then we'll practice with the big graph above. Okay, so the idea is that I'm gonna use red. Okay, so you start at 0 here. Okay, and then you look at the edge outside of this node. Okay, so you consider this node first, and then you see, okay, there is an edge here. If I'm gonna reach this vertex through this edge, I'm gonna reach this guy at time 1, right? Okay, and if you're gonna reach this edge, this guy with this edge, you're gonna reach with time 3. Okay, so this is how we're gonna do it. Okay, so but before we do it, so let's initialize the time that you will reach each vertex. Okay, so this is the estimated time. So let's, in the beginning, we don't see anything. We only know that we're here at time 0. Okay, the other vertex, I'm going to put infinity. When you write code, you don't really need to put infinity. There's a way to avoid that, but you can have a really big number to use as infinity as well. Okay, all right. So let's get started. So you started this vertex, and then you see every edge that is adjacent to this vertex, and you see, okay, if I'm at this, I can reach this vertex at time 1, right? But previously I believe that I'm going to reach this at time infinity, so I have a better timing, so I put 1 here. Okay, and here 3, right? So 0 plus 3 is 3. Put 3 here. Okay, now which vertex I should go next? Okay, we'll pick a vertex and go there and then update, and this is how we're gonna do. Okay, all right. So if you recall, in breadth-first search, we'll meet this guy first, right? So this is 3, but we are not sure if this is like the right number. Okay, but we look at this. So this is the smallest one, so we pick the smallest one. This is like the greedy rule that we have. Okay, and then from here I can see that if I go to this vertex, I'm going to reach it at time 3, which is better than infinity, so I update it. So I update it with 1 plus 2, which is 3. Then this also, I put 2 here. This 1 plus 1, I get 2. Okay, now let's look at what we're gonna go next. Okay, from here I have 3, 3, 2. Okay, if you look at this in breadth-first search, okay, come back to breadth-first search, you can see that we reach this vertex before 3, right? Because breadth-first search just go through the distance, right? So this guy is closer, so I'm gonna look at it first before this 3. So I'm gonna look at this. I recolor it with red. So from here I look at there are 2 edges. If I travel from 2 through this edge, I'm gonna reach this guy in 3 steps, right? 3 the length will be 3, but it's larger than 1, and I already been there, so I just ignore it. Here 2 plus 5, I get to 7, better than infinity, so I update it. Okay, now among the guys that I haven't been there, I have 3, 3, 7, so I pick the smallest one. So maybe I pick this one. You can pick this one and that one. It's okay. The result will be the end result will be the same. Okay. If I pick this one, I can see if I go to this, I'm gonna get 6, but I have already been there with 0. If I'm here, I'm gonna get there with 5, right? So better than infinity, so I put 5 there. Okay, and later on I'm gonna pick this one, 3. I'm gonna update, and I can see that if I'm going to this, I get to 5, and 1 is better. If I go to this, I get to 4, right? 4 is better than 5, so I update it like that, and I update this with 7, I think 7. Okay, I know that that's a path reach t of length 7, but that might not be the best one. Okay, now among the guy that I've been there, I see 4 here, right? So 4, 7, 7. So I pick the one with the smallest label that I haven't been there before. So I pick this one, and I try to fix everyone around me. So 2, 6. I can only fix that, right? So I fix it, and I say I guess to 6, which is better than 7. So I put 6 there. And the last one I picked the final vertex, right? The destination 6. So I know that the shortest path is 6. Okay. Now I know that the length is 6. Okay, but I don't really know the path, right? So we actually need to keep track of the path. How can we keep track of the path? Basically, when we update the distance label here, we have to remember the vertex that update the distance to it. Okay, so like here, when I update this to 1, I remember it's from this guy. Okay, from this guy I get 3 from this guy. This one, or this, let's say this one. This one I get 2. This one 3. Okay, from this one, it's got updated 2 times, right? The first time from 3 and the second time from this. So previously, in the first time it's got updated, the parent is going to be there, but then I update it with from 5 to 4, right? So I need to change it to this. Okay, and so on. So on. And this parent pointer gives you the path. You just travel back, and then you get a path from the root to the final vertex. So that's the Dijkstra algorithms. Okay, so let's recall the idea. You can try to play with this this graph, okay, to see how it works. But I'm not gonna spend time on it. Okay, so I'll leave this. You can capture this and try it on your own. Okay, there's a website again, as I told you last time, the Visual Algol website, and you can find shortest path. This is single source shortest path. Okay. And you can example graphs widths. Maybe that's one. There's a directed there, but it's okay. You can use the same thing. You can try Dijkstra. Okay. The original maybe. So that's the simulation. Okay, you can see that. Okay, but we'll look at the implementation now, so you can watch this later on. Okay, all right. So in class, I think there are basically two ways to implement Dijkstra algorithm. One which takes O n square plus m that you probably learn first. N is the number of vertices. M is the number of edges. Okay, but that will be too slow for our implementation. We'll use data structure to speed up some of this, but let's look at the version, the slower version first. Okay, so if you recall the way I demo the algorithms here, I'm gonna have a set called S, which represent the set of vertex that I visited, or in terms of Dijkstra algorithm is going to be called scan vertex. Okay, so the ones that I pick and I look at the edges out of it. So in the beginning, I'm gonna let it be empty. Okay, and I'm gonna initialize Dijkstra from S. Okay, so from vertex S, this is small s. I'm gonna compute the distance to every vertex, not just the final vertex. Okay, all right. So I'm gonna initialize the for each vertex U. So in the graph, I'm gonna have graph E, and the length. The length will be the distance. Okay, length of it UV. So that's the distance between U and V. So L is going to be a function from vertices, from edges, function on the edges. Okay, so that's the length. Okay, when we implement Dijkstra, we need a way to keep the length. Okay, so now for each vertex, I'm gonna initialize the D to be infinity. I'm gonna say D of S is gonna be 0. Okay, and the algorithm works in steps. Okay, so I'm gonna have a while loop here. We do something. Okay, so the idea is that for each step, I'm gonna pick the nodes that I haven't that is not in S. Okay, with the minimum label here, distance label here. So let U be the vertex text not in S with smallest du. Okay, so in mathematic term, we're gonna say arc min of U, min U, right? Min of U such that you is in V but not in the scan. That minimize the value du. Okay. How can you find that? Okay, you can basically like write a simple loop to find this vertex. Okay, so we're gonna do that later on when we implement the algorithms. Okay, and then we look at when we add here, we're gonna say, okay, I'm gonna scan you. So I add S gonna be S union U. I put U in set S. So this is when I put a red color on the, what is this? Okay, and then I look at each vertex, each edge, UV in the graph. Okay, and then I check if distance of V is larger than the distance of U plus the length UV. So this is like if I go through U, so U is here, this V, is like that, and it's LUV. This is like if I'm here, I'm gonna go through U, I'm gonna get to V better than the previous estimate. Okay, so this is what I'm gonna do. Then I'm gonna update VV to be U plus LU. I'm gonna update the estimate. So basically the loop is gonna be that, something like that. So I'm gonna run this while S is not equal to V. I assume that the graph is connected. So if I haven't looked at every vertex, then I should continue. Okay, so this is the algorithms. Okay, and if you need to update the parent pointers, so you do it here. You say parent V is gonna be U. So this is the algorithms. Okay, so let's implement this really quickly in C++ and see the running and try to submit it. Okay, the running time quickly. This is gonna run for n rounds, because for each round I pick one guy and I put one guy inside S, and that guy will not return again. Okay, so it's run on n rounds, and this step, if you write a simple code to do that, it takes O(n). So the algorithms, just these two parts is gonna take n square, and you look at each edge once, right? So, and here takes time constant, so its running time is n square plus m. Okay, so this is the first one, and we improve it soon. Okay, so let's see the code. Let's see how we write the code for this. All right, so let's get started with the task statement. So it's a shortest path. You're given an undirected graph. So in many cases you get a directed graph, but this problem gives you an undirected graph. So when you have an edge between vertex A and B, you can go from A to B and B to A, and W is the weight. Okay, that is the length. Okay, and the number of vertex start from 1 to n, and you want to find the shortest path from 1 to n. Okay, so I would start with so the first line of the input is n and m, and each line is in this format, A, B, and W. So the vertex A, vertex B, and width A, W. Okay, so you can pause the video and read the task statement to see if you understand, and maybe you can try to draw the graph with this input and see if the output is 17 or not. Okay. All right, so my code, typically let's start with the read input. So same thing. Okay, I need a vector, and then I read n and m, and then for each vertex, each edge, I read u, v, and w here, and I usually start with the index of the vertex with 0, but the input start with 1, so I need to decrease it here. And this two line is the typical one, right? I add it to the adjacency list of U and V. But here I need to keep the weight as well. So I have another vector weight here to keep up with the weight of the input. Okay. So now let's write now I have my graph. Let's write the Dijkstra algorithms. Okay, so let's see, what do I need to keep? So basically I need to keep the distance, right? So that's the distance. I also need to keep the fact that the vertex has been scanned or not. Okay, so that's the two things that I need to keep track of. I also want to keep track of the parent so that I can reconstruct my parent pointer, my path back. In the initialization, I would basically, from each vertex u, I'd say this u is infinity. I still don't have infinity. So so if you look at the task statement, there are 100,000 nodes with the width of 1,000. So the longest vertex will be 100 million, right? So any number larger than that can be treated as infinity. So I just put a billion plus one as infinity. So this will keep my code simpler, but you can do something else. You can put -1, but it's gonna take a lot to implement. Also, you need to look at the task statement to figure out the right value of infinities. Okay. In many cases, you cannot. It will be a pain to do that. Okay. But typically in this class, this number should be fine. Okay. And then I say scan u is false, and parent of u say it's gonna be -1. I'm not gonna use it, the parent pointer for this code, but I'm gonna leave it so that if you need it, you can use it. So I call init here. Okay, and then I start with the, if you look at the pseudo code, same thing here. So I say this of s is 0, and then I'm gonna go into my loop. Okay, while loop. Let's call it while true for now. We'll figure out how to do that later on. And then I say int u, it's gonna be here. I wanna find the one with not the unscanned vertex with the minimum distance, right? So let's call it find min unscanned vertex. Okay, we'll write it later on. Okay, so let's write it here. Okay, that's a template. We're gonna write it later on. So after we get u, we're gonna go through every edge of u exactly like this. So let's say scan u is true. Okay, and go through each edge of u. So let's get the degree. If you recall, you can see that I haven't keep up the degree pointer or degree array. So I need to get it from here. So in d equals 0, d less than degree. Okay, I'm gonna go through the one in the adjacency list of u. So let's say in v, the d one. Okay, I'm gonna also get the weight u. Okay, now my condition here is like, if this 10 of u is larger than going through u, right? It's gonna be, so let's like it here. This u, this v, that's my target, right? It's larger than this 10 of u plus the weight, then I need to update it at this v, this v plus w, and I also keep up the parent to be u. Okay, so that's it. That's the main thing. Oh, I need to find the unscanned vertex here. So let's write a simple code. So min value, so let's say it's equal to infinity first. And I also need to keep track of the min vertex, right, min u. Okay, so for each vertex v, okay, so if not scan, I need v to be unscanned, right? And also the distance of v is less than min val, the best thing that I've seen so far. So I say min val equals this v, and also min u is gonna be v. Okay, min u. So that's my code. So let's see if it runs. Oh, I need to write the main program. So I just read input and then call Dijkstra from 0 and then see out distance n minus 1. Okay, so that's the code. Okay, that's the main Dijkstra loop, and with this function to find the minimum guy. The running time is n square because this would run for n step. Oh, I have y true here, so we need to fix this. So basically, I would keep the counter y counts less than n, and after this I say count plus 1. Count plus 1. This code will not work if you have a graph which is not connected, because it will loop forever. But we'll fix it later. If you can fix it if you want to deal with the case with when the graph is not connected. Okay, because this function you will find something that is not that will be bad. Okay, let's see if it's work. Demo. Oh, demo. I typed it wrongly. Okay, so so that's the example from the test case. Let's see. Okay, 17. Okay, so let's try to submit it. Okay, you can see that you get 50 because it's too slow to get to the full score. The reason for that, if you look at the code here, you can see that the code runs in n square time, and then it's 100,000, so it's too slow. Okay, so let's try to fix it to make sure it's faster. Okay, so the part that is slow is this one. I want to find the unscanned vertex, so I'm going to use data structure to help me doing that. Okay, basically you need a priority queue that keeps the vertex, and you order the vertex by the distance. Okay, so to implement the priority queue, you can do it in many ways. I'm going to use set with pair, so that it will be really easy to implement. So let's try to do that. I'm like explain you later on. I'm going to use include SQL set. Okay, and I'm gonna have my queue here. It's gonna be set of pair of in and int. So the first element in the pair is the distance, and the second one is gonna be the vertex, the index of the vertex. So let me save it fast. Okay, so let's call it queue because it's gonna be a priority queue. Okay, and initially I need to say I need to put s in the queue. So it's then I make pair. The first value is going to be the distance. The second value is going to be the index of the vertex. So I'm going to put 0 and s here. Okay. Okay. I'm going to leave the count here for now. Okay. But find the min unscanned vertex. I'm not going to use it now. Okay. I'm going to just take the first guy from the from the queue. So I need to take the pair. Let's call it du. Then q.begin. So that's the iterator point to the first guy. I need the data, so I need to dereference it, and I need to remove it. Remove the first guy from the queue. Okay, like that. So my vertex u, the du is the first element here. Du dot first is gonna be the distance, and du dot second will be the vertex. So if the u is going to be du dot second, and then I okay, the other is pretty much the same. But now when I update the vertex, the distance here, I need to update the value in the queue, and that will be really hard. Okay, the way I'm gonna do is that I'm gonna, after I find a new vertex, this v, I'm gonna put it in the queue without updating it. Okay, gonna insert make pair again. The first element in the pair is gonna be the distance. The second one is gonna be the index. Gonna do it like that. Okay, but doing this, I'm not gonna remove the old value. Okay, because that's hard. Okay, so the word our queue will contain duplicates. If you recall this picture, let's look at this picture. You recall when we meet this guy, going from 3 to this guy, we get 5, right? And then going from this guy to here, the distance is 4. With this code, the key we put that we put going to be 5 comma the number the index of the vertex, and then 4 comma the vertex of the index. But when you pop out from the queue, you're gonna get 4 first, and then you later on you get 5. So vertex here, U here, will appear many times, although we have the scan vector flag here. So we need to do something here. So we need to make sure that if U has already been scanned, so we are not gonna continue. So we're not gonna go further. We will pick the next guy from that. Okay. So the code will be pretty much the same, but you need to prevent from the code from doing the scan too many times. Okay. If you forget to do that, your code will run maybe run really slowly. Okay. All right. And I'm gonna fix some other thing as well. I'm not gonna keep the pointer anymore. Okay. The counter anymore. I'm gonna just run until the queue is empty. So if the queue is not empty, I'm gonna keep doing that. Okay. Just take the guy and see if you not scan it and update. Okay. So the rest will be pretty much the same. So let's see if it can run. So I only changed the key here. Okay. So let's see. Okay, and let's try to submit it. Okay, it passed. You can see that the code pretty much follow the same idea from the pseudocode. Okay, with some implementation detail here of the queue and here. The other will be it's like I'm taking the pseudocode here and write it in C++. Okay. All right. I'm gonna provide you with this sample code so that you can work on the problem set. The problem set will be I'm gonna explain it in more detail in Discord, and the code will be provided in Discord. Okay. All right. Good luck and have fun working on Shutterstock problems.